already brought a dam model onto the screen. This is just the geometry, just the shape which has been drawn here, which you can see is drawn in volumes. In fact, this was imported, I think, from an IGES file. It's on the file menu under the import function here. If you choose, well, there's a whole range of different import options you've got there, but if you choose the IGES file, you can also, when you pick a file, there it is, you can look in the advanced options and you'll find a whole lot of helpful options to deal with there. But when we've got the geometry already in the model, the next thing we need to do is to break it into finite elements. Everything's got to be broken down into something which can be calculated correctly, and the way we do that is the same whether we're using a beam model, a shell model, any kind of 2D model, any kind of 3D model, and indeed a volume model. We generally, to construct the rest of the model, work down this list, down the mesh, geometric properties, material properties, supports, and loading. If you get to that line, you know you've done everything you need for a linear static analysis. So that's how I'm going to work. I'm just going to work down that list, and the first thing I'm going to do therefore is to break this volume geometry into elements. So I can choose volume elements which are tetrahedral. That will fit any irregular shape. There are also regular options if you have a regular object, but for this irregular shape I'm just going to choose a tetrahedral mesh. I can choose a mesh size and give it a name like volume mesh. When I OK that appears as an attribute over on the attributes tab of the tree view. That's defined the kind of elements that I want to use in this model or in this part of the model. I can have many different element types, of course, but it's defined, but it's not yet assigned. So what I need to do is select which parts of the model are made up of those particular elements, which in this case is the whole model. So if I pick the whole model and I drag and drop that volume mesh over from the tree view on the left to the working model pane on the right, then that assigns that volume mesh to all of the volumes in the model. And it will take about 20 seconds or so. What LUSAS is now doing is breaking those irregular volumes into tetrahedral elements, in fact into about 12,000 elements. So there's a bit of work to do there, but it's done it, as you can see. So you can see how that has been broken down now into elements which can be used for our numerical analysis. As I said, it's the same process then, whatever object you're modeling, be it a bridge component or a bridge deck or a dam like this, whatever it is you're modeling, we keep on working down this list. We don't have to give any thickness to this dam because it's already drawn with a thickness. That's why it's made out of volumes. So I just need to choose a material. So I can go to the material library and choose, say, concrete of some type. I could choose concrete to a particular code of practice or just a generic concrete here. Once again, that appears as an attribute on the attributes tab of the tree view. It's grey because it's not yet assigned. And then I can choose where it is assigned, which again is the whole model. And I drag and drop that across. I keep on going. I need some supports. Now, of course, in a real analysis of a dam, you may have some analysis to give you support conditions, or you may indeed wish to include the soil, the supporting structure, as a supporting structure within this model. But in this case, just to keep things simple, I'm going to create a support attribute which is just fixed in all translations. And I'm going to use that for the sides of the dam and for the bottom of the dam. So I call it fixed translations. And OK that. You'll notice there that there are options to choose lift-off supports and options for contact, which is when a support starts out of contact and then later may come into contact. So you can use those options if you need them. But I'm keeping this one simple. So if I just assign, first of all, to the surfaces down here, we'll see that our little green arrows appear, and that tells me that I've now assigned supports to the bottom of my dam. I need to obviously assign supports to the surfaces at the side of the dam. So probably the easiest way to do that is to rotate the model around a little bit like this, and then perhaps rotate it around the other way. Lots of ways of doing it. I mean, it's just selecting, just using the mouse. And if I select the surfaces down here, maybe so, like so. Okay. I've selected those surfaces, and again I assign supports there, and the same on the other side. So I'm using the rotation tool here just to rotate the model around a little bit to one side or the other, just to get an angle that I think is going to be useful, and then rotating around again like so, and selecting surfaces. Various ways of selecting surfaces and other parts of the model, which obviously as you get to know the software you can find out. It's just to do those, you can find the options. Indeed, I might just select those last two surfaces by clicking on them. There we go, click there, two surfaces selected, there we are. So now I've got supports where I need them in this model. I can just look at the dam at whatever angle, get an idea of how it looks. That seems reasonable to me. I can switch off the little arrows so that I can see the whole dam a little bit more clearly and see what I've got selected a little bit more clearly. And if I just keep on working down this list, I've got supports and now I need loading. Well, in fact, there are lots of loading options in LUSAS, of course, that might be useful here. Temperature loading and distributed loads, face loads, that would be useful for a hydrostatic load. In this case, I'm just going to show you the most simple thing straight away, and that is just to add gravity to this dam. And in fact, that's everything I need to solve this model. So if I just press the solve button, LUSAS will go away and calculate all the stresses through that structure based on the applied loading, which in this case is only the gravity loading. Okay, now I see I've got a colourful icon there. That means that the results are now available, and all I need to do is display some. So if I right-click around my model and choose contours, I can choose to look at the stress, SE. For example, that's the equivalent von Mises stress, and that shows me the most stressed parts of the structure straight away. This may or may not be, I think for a real dam analysis we would need to think a lot harder about the actual loading that's being applied, but you can see straight away that you've got your results for your 12,000 or so solid elements. And of course, now we might start to think, well, the dam is not constructed in one piece. It's constructed one part at a time, one lift at a time, if you like. So perhaps a good thing to show you at this point is a stage construction analysis. Very simple to set up, and the same principle applies whether you're using stage construction with beam elements, with shell elements, with solid elements. It's always the same in LUSAS, the same process. So what I do here is, again, I use the attributes menu where I can define things and then later assign them. And what I'm going to define is an attribute that's known as birth and death, or activation and deactivation. So what I want to do is deactivate a large part of the model. Most of the model, in fact. I'm going to deactivate to begin with. Deactivate will do. We call it deactivate. So at the beginning of the analysis, I can deactivate part of the model, and then later in the analysis, I'm going to, if you like, reactivate parts of the model. So let's call that activate. If I now, I may wish to retain the analysis that I've done so far. Now, I realize this, in this case, I just have a gravity load case. It's not terribly interesting, but it might be that I have a static analysis of the finished structure, which includes all kinds of loading, such as temperature loads and base loads, hydrostatic loads. So what I might wish to do is create a new analysis. So I have analysis number one. I would say, well, let's create a new analysis, a structural analysis, which is called analysis number two. I might just call it, to help me remember, it's a stage construction analysis. I press OK. You can see I've now got the beginning of this location number two, so I might call this pore 1. That's going to be the beginning of my analysis, and at the beginning of my analysis, all of this upper part of the dam is not there. I won't start with no dam at all, because that's nothing to analyze. But what I will do is just deactivate the upper parts of the model, and that leaves me with just the first pore in that load case. And then it's very simple. I just add more and more parts. So if I just select the part I wish to activate, I put that in as pore 2, and then just working on up, pore 3, and so on. You get the idea. So once again, the idea here is that you define your attributes. They appear in the tree view over on the left, and then you assign them by selecting the parts of the model where they apply, and in this case selecting the locase where they apply, and then once you've finished that process, you've got a model which you can analyze. I hope I've counted these correctly. There we go. So the final pore 7. There we go. The only other thing I need to do here is, first of all, to make sure that there is actually some gravity in these locases, which I hadn't added along the way, and also to tell LUSAS that this is now a nonlinear analysis. The nonlinear analysis is needed simply to tell LUSAS that in each step we have to reconstruct the stiffness matrix. All I need to do is tick that box. It's as simple as that. I press OK. Now if I run this analysis, we should find that the stage construction analysis will run through. So it's in effect we're analysing 1, 2, 3, 4, 5, 7 structures one by one, but in essence all the information from one step is carried forward to the next step. So if there was some real nonlinearity in there, some boundary nonlinearity like liftoff, if there was some soil nonlinearity, material nonlinearity of any type indeed, soil or concrete cracking, if there were any geometric nonlinearity like buckling or cable stiffening, those would all be taken into account as the analysis steps from step 1 up into step 2 and so on. What I might do here is just, if I go to the contour layer, I can choose to look at, for example, vertical stresses instead of von Mises stresses, a little bit easier for us to comprehend. And also I can look at the, I can change the contour ranges to maybe something that's going to be standard for all of these different steps. That will show, as we're at the beginning of the analysis, we start with pore 1 here, you can see this part of the model is not very stressed. Then as I add more load above, of course the stresses increase now, nudging towards 250, and as I go on through the analysis, increment 3, increment 4, or pore number 4 if you like, you can see that the stresses are now getting up towards around about 725. So remember that there are stresses in these parts of the model as well. Yeah, going on up, and then as I get to the final increment here, I'll just skip one, we should find we're reaching the top part of the analysis. In fact, if I spin it round, you'll find that it's the reverse face that's got the maximum stresses there. So that gives us a good idea of how the stresses develop during the pouring of this structure. Now, as well as inspecting our results by looking at contours in this way, there are a whole load of slicing options. I mean, I can't go into every option, but one that I thought was quite useful to show you perhaps is to select. If I just select a node somewhere in the model there, that node, it's 181. I don't need to know that, but that's the one I've selected. And if I want to just see what the stress history for that one node is over the construction process, I can press the graph wizard button here, and I can see a time history which starts by looking at the locase. It's going to be, in the graph it's going to have the locase along the X direction, and then in the Y direction I can choose to see a particular result. So let's say the vertical stress. And as you can see, it's already filled in this box for which node, the node that I selected with the mouse. I press next. Let's call this locase ID and stress SZ. And when I press finish, we'll see that the stress at that location over the locase just increases and increases. Obviously it's in a negative direction here because it's becoming more and more compressive. So it starts off around about 50 and it ends up around about 210. So that gives us a good idea what's happening in some specific part of the model. So that's a nice way perhaps of looking at your results. Another kind of nice tool which you might wish to use is, let's just turn off the geometry as well here. Oops, I'll turn off the geometry there. Yeah, another nice option here is to maybe animate the model so that we can see what's going on. Okay, yeah, let's do that. If I go to the Utilities menu, there's an animation wizard. This is particularly useful for perhaps demonstrating to a client what you've done during an analysis. Oops. So if you choose the load history option there, you can say I would like to see the results from analysis number 2 in a sequence. When I press finish, what it's obviously doing is compiling the results for each load case in turn, and then it will put that into an animation which we can then save, put into Excel, or show to people in any way that we wish to send them as an AVI file, for example. So hopefully that gives you a kind of idea of how the wizard works, the animation wizard, and how indeed the stage construction process can be analysed. Okay. I could also show you a little bit about heat of hydration in dams. I don't know how much dam work you actually do, but perhaps it's worth, I'll just open a model which has got some heat of hydration in, just so I can show you roughly what's available, or very briefly what's available, I should say. So this is just an example model, but the principle is exactly the same. This is a dam which is in 3 lifts. I can see the analysis has already been undertaken, but the important part, the different part, if you like, of this model is that within the concrete material, as well as having elastic properties here, you can just tick a box and have thermal properties. The thermal properties then allow you to input the thermal conductivity and the volumetric heat capacity. That's the energy required to raise a unit volume of the material by 1 degree in temperature, which I suppose you can see by looking at the units here. They're in joules per meter cubed Celsius. And then down here, because we have concrete, it's exothermic. I have a weight of cement per unit volume, and I can choose what cement type I've got. Obviously, if you get into doing this kind of analysis, you would need to go and read up what each of these parameters are for, or look in the Eurocode in EN 197 and in the manual here. But essentially, there's just 5 or so parameters there. On top of that, I need to tell LUSAS that the temperature loading will be free. That is, it's possible for the concrete to change its temperature. It's not fixed, which would mean that the concrete is held by some means at a certain temperature, by cooling it down with pipes or so on. And on top of that, I need to put in some thermal conductivity or convection coefficients for the surrounding air and the surrounding soil. So that gives us some information about how the transfer of heat passes between the concrete which is producing the heat and the surrounding air or the surrounding soil. And with that little bit of extra information, we can do not only a structural analysis, and in the structural analysis we can look at stress results just as we have before, but down here I have another analysis which is a thermal analysis. And in the thermal analysis you can see I've got results already, so I can look here at the end of stage 1, perhaps if I just step through briefly, you can see at the beginning here I've got quite high temperature, which is 25 degrees, and then as I step through it increases as the exothermic reaction increases, and then as I go towards the end it's starting to cool down again. If I then look into the second step, you can see the exothermic reaction again, and so on. So you can see how the temperature is changing, and obviously then you can look at the correlation in terms of stresses in the concrete. So if I go back up to the structural analysis, this is the stress, if I look at the contours of stress indeed, the stresses which are arising as a result of that difference in temperature and the particular support conditions and so on which I've input in this particular model. So that gives you just a quick overview about how the thermal analysis can be useful for heat of hydration of concrete. It's not a training course. I'm sorry I can't give you more detail, but hopefully it gives you a little bit of an idea of the capabilities which may be useful to you.